today we are going to begin our discussion by talking about wave packets, which are essentially regular and non-dissipative. That means, the wave packets will keep appearing in space and time at regular intervals. This will be followed by wave packets, which are essentially singular in appearance, in the sense that they will be aperiodic. This can also come about because of the damping present in the system. And as we said that when it comes to waves, we do not distinguish between hyperbolic or dispersive waves. So, we draw an example of a dispersive wave from surface gravity waves forming over liquids or fluids or water. And what we find that the creation of the waves does not require the governing equation to be time dependent. That is why we have specifically chosen this particular problem of surface gravity waves, because the governing equation is a Laplace's equation, which is time independent. The space time dependence of the wave propagation comes about through the boundary condition, and how this boundary condition affects, that is what we are going to talk about with the help of this kinematic boundary conditions. And this auxiliary condition sets up the waves, and then we will talk about specifically various forms of surface gravity waves, how the trajectories are of individual particles. We also would like to relate its space and time dependence through what is known as a dispersion relation, that is a relation between the wave number k and the circular frequency omega. This is what we would establish for the surface gravity waves. We can further classify the surface gravity waves into two, depending on the depth of the waves. So, we are talking about either shallow or deep water waves, and we will see how the particle paths are different for shallow and deep water waves. We will also notice one particular aspect of this dispersive wave is the existence of group velocity. Group velocity is distinct from the phase speed, because the group velocity is important, because this is the speed at which energy flux is created in the flow. Basically, I thought that you are familiar with waves, but it is mostly done in the context of maybe optics or acoustics. So, here I thought I will give an example of the mechanical system. So, waves in fluids happens to be a very well researched topic. People have been looking at it much longer than any other field, and probably you could be able to relate to other fundamental concepts of energy and its propagation, etc. So, I thought a geophysical fluid dynamics example would be quite in order. Okay. So, please note down that I am mostly following this number 1, and it is a very decent book. There is a South Asian edition available also in the market. So, if you want to have a book of this kind dealing with fluid mechanics in general, it is a beautiful book. You can really take a look at that. The second one is a classic, this is written by Sir James Lytle. We owe most of our current state of knowledge to people like Lytle, Witham, those who have contributed in the last century. Of course, prior to that you have giants like Stokes, Boussinesq, Rayleigh, they have contributed. But this one should be more than adequate for you to understand what we are doing. And some of the things I am doing it from the numerical perspective. So, you will have to pick it up from some book on numerics. So, yesterday we were talking about systems where we have not necessarily a single harmonic content, but you would have the presence of a continuum of wave numbers. And if you have that, then we were trying to figure out what happens when two neighbors interact. So, the neighbors here are characterized by the wave number k1 and k2. The corresponding circular frequencies are given by omega 1 and omega 2. Their differences are given by dk and d omega. So, when we look at their superposition, we find that it's composed of two factors. The first factor gives you an amplitude that varies slowly with a wavelength of 4 pi by dk and a time period of 4 pi by d omega. Whereas the second factor is nothing but a small variation of the original harmonic elements which are given here, right. So, what we notice that two neighbors interact via superposition to give you a slow modulation of amplitude, and that gives you a kind of a phase variation given by this argument. And if you want to track constant x by t line, that you can see, you would be doing it by following d omega by dk. And so, what we find that the amplitude moves with this speed, right, this Vg, and since amplitude is proportional to the energy, or the other way, energy is proportional to amplitude squared. So, this velocity is the characteristic velocity of the propagation of energy itself. We will show it with the help of some examples why that is true in a little while, but let us first of all try to distinguish what we get by looking at waves and wave packets, right. So, on top what you are seeing is a simple harmonic wave, and which is characterized by, let us say, this wave number that we have plotted here for k1 equal to 20, and this is the way the signal varies with space. So, that cos k0 k1x is plotted here. Now, what we did as shown in the previous slide, that if we look at interaction of two neighbors, so that is what we try to do here. So, what we do is we take two neighbors of wave numbers 20 and 21 and see what happens, and this is what you see. Okay. So, this is what you are seeing, that embedded inside each of this packet you have a harmonic variation given by this, because that is characterized by some wave number, that is 20.5. Those are those rapid variations inside, and the amplitude envelope is given by a wave number 1, right, the difference between k1 and k2. So, this is what you would see. So, if I were to be communicating a signal, then which one would be better? If I want to send a signal of, let us say, wave number around 20 or 20.5, which one would be better? Should I send it as a wave or should I send it as a wave packet? Wave packet. Why? You see the presence of these nodes and antinodes. At antinodes, of course, your amplitude doubles, whereas at the nodes they come down. So, you will have to basically see the energy carried is what in this two. You can compare, right. I can compare that if I try to send two signals separately at 20 and 21, what will be the corresponding energy, and I can find out what will be the energy here if I send them separately. So, what we may come out with a conclusion that you may not be able to get a tremendous benefit, because energy is proportional to amplitude square. So, here it is a 4-fold increase at the antinodes, right. So, whereas it can come down to almost 0 in the intervening period near the nodes. So, you have to do that accounting and come back and tell me which one is better. I will look forward to that answer. So, that is one way of communication where we can send the monochromatic waves, or we can send it as a kind of a packet. But there is another way signals are quite often transmitted. Those are when the signal is embedded in amplitude envelope, which renders it aperiodic nature. So, what happens here we have the basic signal cos 20x, let us say, then we modulate its amplitude by this Gaussian function. Okay. Then what happens is the signal information that you are carrying still corresponds to 20x, but its amplitude decays. So, what happens as a consequence, you would have almost zero amplitude outside this single packet. So, this is now from a multiple packets of the previous slide, you have come to a state where you have single packet, and by designing your system, by choosing this exponent, here I have shown you as 8, if I would have increased the damping and brought it to 32, then I would find that it will decay much more rapidly. So, the envelope size comes down in proportional to this exponent, right. So, what we find that such a signal, if I try to pass through the continuum, I would be spending less energy, right, because if I try to send this original signal, it is going to continuously suffer attenuation and decay, various other sources of decay, whereas such an aperiodic wave or a damped wave packet is going to be rather very good to do that. In fact, later on we will come back to another topic where we will see how signals are even transmitted as a single wave, solitary wave, which may actually look like this envelope, and that is what is called a soliton. We will talk about soliton, and you would note that soliton is quite often used to transmit optical communication signals by pulses. Okay. Now, let us get into some detailed look into one such mechanical wave that is created over a vast expanse of fluid, and you have a fluid at rest, then you just give a kind of a disturbance on the surface. So, the surface will be deflected, and let us say we have contrived to create a single harmonic wave here, whose wavelength is given by lambda, and this surface wave that we are creating on the surface is forming over a layer of liquid of height h, and the deflected contour is given by eta of x and t. So, in this exact plane, we would like to figure out what happens, how these waves are generated, what are their properties. That is the topic of our discussion today. To make the arithmetic, the mathematics simple, what we would be looking at is really a small amplitude wave. The small amplitude means the slope of the wave is small, that is given by a over lambda. A is the amplitude of the wave. Okay. So, that is small, and we would also be talking about this amplitude are so small that they are insignificant as compared to the depth of the liquid. Okay. To make things furthermore simple, we will ignore the effect of viscosity. So, no viscous losses, and we are talking about surface gravity waves, and if we look at the ones that you generally see in lakes, rivers and ocean, if you are not looking at very long wavelength cases, you can really neglect the Earth's rotation effect that shows up through the Coriolis term. Okay, now, what do we get? Mistake. The governing equation here comes from the mass conservation equation, that is del dot V equal to 0, and where V is essentially for a rotational flow, we can write it as a gradient of a potential phi. So, it here and you get equation 15. The Laplacian of phi in that exact plane is going to be 0, and the velocity, as I noted here, the components are given as the x component del phi del x, and the z component is del phi del z. Now, you are considering formation of wave over a flat surface. This is my mean undeformed datum, and in this direction we are plotting z, and this is where, let us say, the wave is forming. So, basically we have this surface at z equal to minus h, and that is at the bottom. What do we expect there? That there should not be any normal component of velocity. Since we are doing inviscid analysis, we will allow a tangential component, but no normal component. So, the first condition 16 corresponds to 0 normal velocity at the bottom of the bed. While at the free surface, at the mean position, we will just simply say the fluid would not leave the surface. It would not go out and form a bubble here floating in the air. That of course is possible and feasible. People do it in multi phase flows, but we will not talk about it, because here of course ostensibly we will have wind here blowing, and we do not worry about its contribution to the dynamics of this wave in the analysis that we are doing. So, at the free surface, we will say that the fluid particles would not leave the surface, and this interface equation, as I told you, is given by eta of x t, that is your z. So, what I can say is I can define a function capital F, which is nothing but eta x t minus z equal to 0. That defines the interface geometry. When of course the interface deforms, then what we would expect that its total derivative would be equal to 0, where the total derivative is given by the local path, the local time variation path, and the other one that could be caused because of the motion of the fluid itself. That is the convective path. Okay. Where of course you know that the fluid particle velocity on the interface, that could be written in terms of its component dx dt and dz dt like this. So, what you notice that this equation, that 17a that we have written, actually can be written as a vector equation of this form. So, gradient f dot vb plus del f del t equal to 0. Now, if I define E hat as the unit normal on the interface, then the condition that we have said that there is no fluid through. So, what will happen is the velocity of this fluid particle, that is Vb, and V is the velocity of the interface, they would essentially be same. So, there is no discontinuity. So, that means the dot product of that with respect to E cap equal to 0, where of course, if f defines the interface, E cap is nothing but gradient of f divided by the modulus of that gradient. So, we can see that at the interface V equal to Vb, so we can replace that Vb by V. Okay. So, basically trying to mix up Eulerian and Lagrangian description that we have decoupled. Here it was coupled because Vb was a Lagrangian velocity, whereas this V is the corresponding Eulerian description. So, that is what we simplified here, and what we also note that f interface was given by eta x t minus z. So, if I try to find out what is del f del t, will be simply nothing but del eta del t, and the gradient of f will you can see is going to be eta x. Okay. So, that will be del eta del x, and this part will give me just the k component. Okay. So, del f del z will give me the k component, and that is what we have written here. Gradient of f is eta x, means that the partial x, and plug it in there, and then you get this expression, and this is at the deformed height. So, it is to be applied at z equal to eta, but as I told you that we began this analysis saying that we will be doing some kind of a linearization, looking at small amplitude waves. So, what we would be doing is we will be making some additional simplification that this condition that I am applying at the deformed interface would be reflected back on the mean interface. That is what we are saying, that that condition will be transferred to z equal to 0. And if you look at the last equation, this middle term u into eta x is a kind of a product term. Every quantity here is small, right. So, del eta del t is small, w is small, but you look at this is a product of two small terms. So, that also we can neglect in a linearized analysis, and that is being said here, that u eta x is negligible. So, what happens is the condition that we had written, del f del t equal to that gradient of f times v equal to 0 simplifies to this condition. Okay. This is a consequence of linearization and transposing the boundary condition at the mean interface. So, with those two conditions as an additional approximation, we arrive at this auxiliary condition at the mean interface. So, now what we have two conditions. One condition is as we wrote it down, that w that is equal to del phi del z equal to 0. That is your equation 16 that we are referring to here, and in addition we have this condition del eta del t at the mean interface. So, these are two kinematic conditions. Now, in addition, we would also like to derive some conditions which originate from the governing equation, right. So, those are called the kinetic conditions, and that comes out from the governing equation simplified for the present purpose. So, governing equation, generic equation is the Navier-Stokes equation, and with all these assumptions that we are making about irrotational flow, small amplitude waves, etc., will allow us to simplify to Bernoulli's equation. So, if any of you are interested, these are the steps that you follow. So, equation 23 is your Navier-Stokes equation, and to simplify it, what we have done here, basically this convective acceleration term that appears here is replaced by this vector identity, and you can notice that this is nothing but gradient of v square by 2, and that is what is written here, and this term del cross v is the vorticity omega itself. So, that is what you get. So, this is another way of writing out the Navier-Stokes equation that we keep solving all the time in fluid mechanics, aerodynamics, etc. So, now what we are going to do is we are going to simplify this equation. Simplification will come about by omitting the viscous term that is explicitly there, right. Then we will also say that the flow is irrotational. So, omega is 0, right. So, this term will also drop out, and v as we have written is a gradient of phi. So, this equation that here we have, we will write it as del del t of gradient of phi, and this term we can put it on the right hand side, and suppose the body force is coming through the gravity. So, that f is nothing but gradient of g z, and this is what happens to your Navier-Stokes equation, right. So, this term comes from the del v del t term, this comes from the body force term, this is the pressure gradient term, and this is one part of the convective acceleration which survives after irrotational approximation. So, this is what you have is the spatial gradient of that quantity is 0. So, you can integrate, and this is what you get. This is the general form of Bernoulli's equation that you may have done if you have taken any course on fluid mechanics before. This is little more general because we are talking about the unsteadiness of the flow as well. Now, what you can see that if you are doing a linear analysis, then this could be actually put in this term. We can redefine this phi to include that f1 term, and of course, this last term, these two terms are basically nonlinear because u square and w square. So, that you omit and you get this as the Okay. So, this is your Bernoulli's equation. Now, I was expecting that some of you would quiz me on the fact that here the governing equation is the Laplace's equation. So, what happened to the discussion that we had made about boundary conditions? How many boundary conditions we are talking about? Why we are going through all the steps of various conditions we are seeing here? What is the domain here? See, we are looking at this flow problem in the xz plane. If I want to compute, so in the fluid part, z is restricted between the deformed interface and the bottom. What about x? Anyone? What about x? What is the range of x that you are talking about here? Wavelength. Well, basically we are talking about waves getting created. So, it is a basically unlimited domain problem. So, x there are absolutely no limit. So, what we are looking at in a sense a unbounded domain in the x direction, and we are looking at a system which is not visited upon by losses because viscous terms have been omitted. Okay. So, we can afford to take a very large domain, and then what happens is we can look at the dynamics of the flow in the z direction, and that is why we are struggling with getting some condition here, some condition there. So, in a sense, in the back of our mind, we are thinking in terms of some kind of separation of variable, and that is why we are looking for some kind of two sets of condition, one at z equal to 0 and another is z equal to minus h, right. That is what we are going through, and you are seeing that it needs a little bit of care here. Okay. So, what happens is we also look at the pressure variation in terms of some datum. So, datum is given by rho gz. What we could do is above in the air part of the problem, we could put that pressure equal to 0. Okay. So, that is your datum. So, then what happens is the excursion of pressure would come through this term. One is due to the variation of the velocity field because of this unsteady deformation here, and the unsteady deformation also brings about the change in potential energy. So, that comes through that term. So, what happens is, because we are doing linear analysis and we said that we are going to transfer the condition from z equal to eta to z equal to 0. Okay. So, these are the things. So, what happens is, now we have three auxiliary conditions to solve the governing Laplace equation. Well, I already answered this question. So, you know the answer, that we are thinking of solving a problem which is unlimited in x direction. That is why we are using a trial solution of this kind, a cos of kx minus omega t. So, x can go from minus infinity to plus infinity. We are not restricting there, and a is some kind of an amplitude of that surface wave, and eta is that surface interface displacement itself. Okay. Now, this is rather interesting. You know, many a times in computing, just because some terms do not appear explicitly, you cannot forget about it, and that is why this example is also a very good one, because we saw the governing equation is a Laplace's equation. There is no mention of the time variation there, right? But we know the problem that we are trying to solve has this unsteady variation of the interface. The surface waves are getting created. So, that is what you will have to keep in mind, that just by looking at a governing differential equation, do not make up your mind in thinking what you are solving. Here is a case, time is implicit, and that is why what we have done is we have used that we have used the trial solution where time appears explicitly like a wave pattern. That is what we saw in the D'Alembert solution yesterday, right. If I have a wave, it will have the argument going like this, a combination of x and omega t. They would not appear separately, they have to come together to have a space time variation as a wave. Okay, so if I now look at this space time dependent problem, now what I could do, as I told you, that I would like to write it in terms of a wavy part, that is the wave propagating in x and t, and its amplitude would be a function of z. It will depend on at what height you are looking at. You substitute this in your Laplace's equation, you get this ODE, and that would give you straightforward the solution f of z as combination of two exponentials, and these two constants can be figured out this condition, that del phi del z equal to 0. So, if I plug that in, what I would do is that should imply del phi del z equal to 0 would imply df dz equal to 0 at z equal to minus h, and you plug that in, that will give you this solution. Okay. This condition relating B and A. Now, recall also that we have worked out the interface. The interface condition was given by what? We wrote it down that the condition that we would like to apply would be del phi del t plus g of eta equal to 0 at z equal to 0, right. So, what I do is I have the trial solution phi, so I try to find out what that del phi del t is. So, that will give me minus omega f, right, and g of eta will give me g times a cosine this. So, that would give me this solution, right. All of you can see that. So, it is basically application of this condition using the expression for phi here and eta as we have written down. So, you substitute and you get the equation there. So, you have obtained the value of A and B as written here, and put it back there, because you know what that solution is. A e to the power plus kz plus b e to the power minus kz. You substitute it there, and you would find that those will give you this hyperbolic functions, right? Cosine hyperbolic function and sine hyperbolic function will come in the denominator. Okay. Having obtained the velocity potential, you can calculate the velocity by differentiating it with respect to x to give you u. Differentiate this with respect to z, you will get w. And what is left? What is of course left is that kinetic condition, right? The kinetic condition would come about. I think I have misguided you. That is what happens when you are in a rush. Sorry, this is not, this is the kinetic condition, and I mixed it up for you. Sorry for that mistake. Let me just work out how do I get that. Okay. See that kinematic condition that we had at z equal to 0, that was written down here, 22. So, that was your del eta del t would be equal to del phi del z. And eta of course is a cosine kx minus omega t, and phi we are writing as a e to the power kz plus b e to the power minus kz, and
sine kx minus omega. Now, del eta del t would give me minus a omega and this one will give us, we will have to apply it at z equal to 0. So, that will give us a of k minus bk, and this will of course remain as it is. So, I suppose that gives you that condition 28, right. So, you just knock this off. So, you get a omega equal to k times a minus b. Sorry for that mistake. Now, we have taken care of both the kinematic condition to derive a and b, and what is left now for us to really explore the kinetic condition. The kinetic condition is the Bernoulli's equation that we have written, g of eta equal to 0, and we have the expression for phi, we have the expression for eta. So, we can figure out del phi del eta would be minus a omega square by k and cos cosine hyperbolic k times z plus h by sine hyperbolic kh and cosine kx minus omega t. Okay, so that's that. So what you are getting from here then will be minus a omega square by k, and there is a cos part here. I will not write that thing down. I will write the rest of it. Okay, and plus g of a equal to 0, and that basically done tells you what we are going to get is this we are going to apply at z equal to 0, right. So, this will simplify to cosine hyperbolic kh. So, what we are getting is a also goes off. So, we are going to get omega square equal to g k and sine hyperbolic by cos hyperbolic, that will give us tan hyperbolic kh. Okay. So, this basically tells you what this relationship between omega and k are. So, what you do is you write down this expression as we have done here in 32 that relates your omega with k. So, this is what we call as the dispersion relation. Recall? Why did we call dispersion relation? We will shortly discuss. What we notice is we are relating the time variation with the space variation in the k omega plane. Your governing equation did not have that information because that was a Laplace's equation. See, the reason that we went to k omega space is because our physical space does not allow us to have that information. There is no explicit dependence on time from the governing equation. And how did we get this? All of this came through those kinematic conditions and the kinetic conditions of space, which was time dependent. So, the boundary conditions, time dependent boundary conditions gave rise to this. So, this is what we have been talking about for quite some time now, that space time relationship is often obtained not from the governing equation, but also through the boundary condition. And here is a crystal clear example of how it happens, right? Yes. this is a mistake. This should be capital H. As I have done it here, this is a correct expression. Give me. That's why I have not loaded the notes yet. After teaching all this, prune out all these small mistakes, and then it will be loaded maybe tomorrow. Okay, so this is what we call as the dispersion relation, and now we should be talking about what dispersion is. But for this surface gravity wave, you can talk about the phase speed. Phase speed is by definition omega by k. So we get this. Now you can also distinguish two cases of this surface gravity wave. Consider the case where it is forming over a very, very deep layer of liquid, so that h by lambda is very large, and then what happens? Tan hyperbolic h takes the asymptotic value of 1, and then this part is 1, so you get C equal to g lambda by 2 pi. So that is for your deep water wave. And for shallow water on the other extreme would be where h is negligibly small, so that tan hyperbolic h can be approximated to kh, and if you do that, you notice that the kk will cancel out and you get this. Now, I waited this long to explain to you what is the meaning of dispersion, that you would see if you compare this expression given in 34 and 35. In 34, what you are seeing, that C is a function of k. So different k components will have their phase varying at different rate. Whereas, if you look at the shallow water case, all k components will go at the same. So what happens? Initially, if I create a small disturbance somewhere, all its harmonic components will travel with the same speed. A shallow water case. If it's a shallow water case, then whatever may be, I have created an arbitrary disturbance like this, let's say. So this is my, say, x, and this is, let's say, f of x. Now, given this function, you can immediately convert it into its wave number component, right? And you would probably find that this is a sort of a function like this, or I mean, it's whatever it is. Let's say it is like this band limited, but it is essentially near the origin. So what is the situation with a shallow water wave is all of the k components will be traveling with the same speed in terms of its phase. Now, what will happen then? You would notice that this initial disturbance, each harmonic component going at the same speed. So at a later time, you will see they will be in the same phase relationship as they were at t equal to 0. So that means what? Initially, if I have a compact disturbance, it remains compact. It does not spread apart. That's your dictionary meaning of dispersion, right? It has not dispersed. So that's the reason that we have not mentioned what exactly we mean by dispersion. Only with an example here, we can very clearly see that if c, or the group velocity, becomes a function of k, then different components will travel at a different rate. And initially, whatever may be the their locations are, they will disperse with respect to each other. So that's what we mean by saying that shallow water waves are non-dispersive. Okay. So what happens is, it's in almost all physical system which displays the presence of waves, you have to have this first responsibility to really find out whether the system is dispersive or non-dispersive, and then you can come out with your computation strategy to follow that physical trend. This is one of the way that we go about computing. Now, let's now look at some of the other interesting aspects of gravity waves. we have the expression for phi. Well, it is somewhere there. I have written del phi del t, but phi is there. So what we could do is we could try to find out what these particles are doing on the interface, or anywhere in the fluid for that matter. That we can find out by fixing our gauge on an equilibrium point, which I may call as x naught and z naught. Now, let us say it has been perturbed, and the perturbed coordinate is given by x naught plus xi naught and z naught plus eta naught. This perturbation, of course, comes about associated with a velocity u, that is the partial of xi naught with respect to delta t, and w the partial of eta naught with respect. Why did I write partial here? Why shouldn't I write an ordinary derivative? See, this is something like your coordinate, and I am finding out its time derivative. Wow. Basically, what we are doing, while we are noticing the coordinate of the particle, but we are still keeping x naught and z naught as fixed. So, we are looking at that particle whose equilibrium location was given by this. So, that is why I wrote this. So, although it is a kind of a Lagrangian description, but we still talk about a partial derivative. Okay. Since we have phi expression, so we can get u, that is this. So, that is your u velocity that we have noted, and similarly the w velocity is this, and they are related to this del xi naught del t and del eta naught del t. So, what you can do is you can integrate and you get these two expressions. Straightforward integration would give you those two coordinates, and the locus of xi naught and eta naught will be obtained if you eliminate xi from this solution, right. So, if I just simply find sin square k x naught and this, so that way we have eliminated the equilibrium coordinate and t, that will be all in terms of given in terms of z naught and a, the amplitude of the wave, and you can very clearly see this defines an ellipse, right. The ellipse is given by this semi major and semi minor axis, and you notice that as you go towards the bottom of the liquid, so z naught is going to progressively go towards minus h. So, what you would find that both these axes are going to decrease, because if the argument comes down, both cosine hyperbolic as well as sine hyperbolic reduces. And you can also see at the bottom, of course, it will all become 0, right. Whereas, if you look at all particles on same vertical column, they would be all traveling with the same phase. That is what is also implied in this equation of Phillips, right, because they are all in same phase. Okay. So, coming back to our introduction to group velocity, we have obtained the dispersion relation, which is omega equal to square root of gk tan hyperbolic kh, differentiate it with respect to k to get the group velocity, right. And I would, if you want me, I can derive this, but it is straightforward. You can work it out. And now you can again look at this group velocity value for deep and shallow water waves. For the deep water wave, of course, kh goes to infinity. So, sine hyperbolic kh goes to infinity. So, this will the second part will go to 0. So, you will get the group velocity as simply c by 2. Whereas, on the shallow water wave approximation limit, sine hyperbolic 2 kh would approach 2 kg. So, this will give you 1. So, 2 will cancel with 2 and you get this. So, what happens is you notice that the energy in a deep water wave travels slower as compared to the phase speed, whereas for the shallow water wave they are just the same. And you also notice that problem that we had looked at, that 1D wave equation. If we would have looked at solution some amplitude well plug cos kx minus omega t, this also will give you omega equal to kc, and if you calculate d omega dk, you will find that is equal to c. So, that is your so this is an example where you can see that Vg does not depend on k. So, here is a model equation which you can employ to figure out how your numerics is doing, because your physical group velocity tells you that if you create some kind of initial condition, it should remain the same, it will simply translate to the right. If you try to solve it with a bad numerical method, you can see that even if you give a sort of a wave packet, it will break apart because of the problem of the numerics. So, that is something we should look at. So, group velocity is a very good indicator for us to judge if our numerical method adopted is a good one or not, because that is the speed at which the energy of the system travels. That is much more important, right, for us to understand. Now, this part, let me see if I can quickly zip through and explain to you what exactly we are looking at. Next, I made a statement here what the energy flux is happening when we have this kind of a wavy disturbance at the interface. If I look at a wavy interface, now the energy flux would be created because there is a pressure excursion. So, pressure is varying as you go along in the x direction. Okay. So, what we could do is, if we keep our attention fixed at a particular, say, at a perfectly harmonic component, and this is your x equal to 0. So, what happens is, we are saying the energy flux across this plane will be the pressure work done by the fluid in this part, and pressure the work done on the fluid on this part. So, this is your x equal greater than 0, and this is this, and this energy flux we can work it out in terms of pressure times the velocity integrated over the whole height. So, you can imagine this is your bed. So, you are basically integrating over this whole range. That is what this limit tells you. This is the pressure times velocity gives you the energy flux term, and if we are talking about a time averaging, so this angular bracket indicates a time averaging operation. Okay. Now, pressure, as we have noted, comes about from rho g, rho g z plus, say, from fluctuation term. So, this is your rho gz term plus some the fluctuating pressure. So, this is your mean component. So, if I substitute it there, so I will get 2 components minus h to 0 will be the fluctuating part, and we'll get so if I do a time average of this, it will reflect on this, and this time average itself, if I am looking at perfect harmonic thing over one wavelength, this will go to 0. So, all we need to do is look at this, and if you recall the Bernoulli's equation we wrote, there the fluctuating pressure was given like this, and whatever we had here g eta, so this is the mean part, that is what we have written there. So, that part is gone. So, if I leave it like this, so p prime works out as rho del phi del t, and phi expression that we have written down, and what we will find that no, this is okay. This is okay. Here will be minus. Okay. So, since we have the expression for phi, we will get p prime would be equal to minus rho times del phi del t. So, we have that expression, we will get rho a omega square by k. Okay. So, basically if I now look at this flux term, then will be p prime times u. So, u also we have written down the expression before. Yeah, we have the expression of u here. So, we can plug that expression for u, and we have the expression for p prime, and we look at this. So, that will find both of them will contribute a cos of kx minus omega t. That is the time varying path. So, time averaging will relate to that. So, that will be cos square, one coming from p prime, one coming from u, that will be that, and we have rho a square, a will come from u also. So, this and this expression would come here. In addition, I will just please allow me to write this term. Sorry, this will come here. What will contribute to that? Okay, I think I will stop here. I will wrap it up in the next class. So, we'll work out a couple of more steps, and that will continue.